Okay, a pleasant afternoon, everyone. Welcome to physics class again. So this afternoon, we will talk about something related to force that we just talked about last time in dynamics. So, do you have any idea? Okay, to start. So as what I said, our topic this afternoon will be related to force and also to this picture. So do you have a guess? Try to guess. Okay, so our topic this afternoon will be about turning effect of forces. So are you ready? Okay, I guess you're all ready. Let's now know the objectives about turning effect of forces this afternoon. So our objectives this afternoon, we are going to describe the turning effect of a force and the conditions needed for an object to be in equilibrium. So familiar? Another thing also this afternoon, we are going to calculate moments, forces, and distances. So are you ready? Okay, let's now proceed. So first we have to define what is moment. Have you ever encountered this one before? I guess so. So when we talk about moment, how do we define moment? So first thing, first idea about moment, turning effect of a force about a pivot is called moment. So in short, moment is the turning effect of a force. So we call it a moment. That's how we define rather a moment, a turning effect of a force. Another thing also, moments are described as clockwise and anti-clockwise depending on the direction of the force. So again, moments are described, or it is being described as clockwise and anti-clockwise. Later on, we will be using that one, especially in solving, especially in the concept of equilibrium. So, another, the moment of a force is also called a torque. So do not forget that one. A torque is also known as the moment of a force. So do not forget the concept of a torque. You might encounter this one in A level. That refers to the moment of a force. Okay? So let's now go to the examples related to our everyday life examples of moment. So we have an opening a door. So opening a door is an example of moment in our everyday life. So as you can see in the picture, that shows moment. Another thing also, or example of moment in everyday life, is loosening and tighten, not using spanner or wrench. So you can see in the picture. So that is an example of a moment in our day-to-day life. So another example for moment, lifting a load with wheelbarrow. So lifting a load with a wheelbarrow is an example of moment, or it shows moment of force. So another example is lifting a heavy object using crowbar or lever. So you can see crowbar, or using crowbar or lever. This one, lever, and then the fulcrum, man lifting a stone with a lever. So these are examples, or some examples of moment in force. So now, let's go to this one. Moment of a force can be calculated using the formula. So I know you're familiar with the formula in computing or calculating the moment of a force. So it can be calculated by this concept or formula. We have the moment of a force is equal to the force. Again, moment of a force is equal to the force multiplied it by the perpendicular distance from pivot to force. Or it can be denoted in this symbol as M is equal to F times D. This one, the formula, where M is your moment of a force, F is your force, And D is your perpendicular distance from pivot to force. So I want you to remember the formula because we will be using the formula later on as we go to solving. Another thing also, or important concept in here, the unit of measurement for moment is Newton meter. Again, a moment can be measured, or the basic unit of measurement for moment is Newton meter, or denoted it as Nm, or Newton centimeter. We can also use Newton centimeter or NCM as a unit of your moment. You just choose which one do you like. But it depends upon the question or given at the end of the day. Okay, so I hope you'll be able to remember this one. And I guess some of you have the idea about the formula for the moment of a force and also to the basic unit of measurement of it. So do not forget, it is measured in Newton meter or Newton centimeter. That can be solved using the formula M is equal to F times D. Okay, so the moment of a force can be increased. How? How can you increase the moment of a force? Actually, we have two ways on how we increase the moment of a force. The first one, class, is by applying higher force. So by applying higher force, you can increase the moment of a force. Next is increasing the perpendicular distance from pivot. So once you increase the perpendicular distance from a pivot, then you increase the moment of a force. So I want you to remember these two things or two ways on how you increase the moment of a force. So are you following? I hope you are still there listening. So now, let's go. Let's go to the example or work example. Let's try to apply the formula so that we can appreciate how to use the formula in a given problem. So let's start with this, work example 1. So our problem or our situation in here is a boy loses the knot using 0.25 meter long spanner. He applied 50 Newton of force on the spanner. Now, our task is calculate the moment of a force produced. So do you have any idea? I guess you have, since you already you already encountered this one before. So this is just a recap about what you have learned before. So now let's identify the given. We have 0.25 meter. We all know that this is our what? Our distance, of course, our D. And we also have a given 50 Newton. And we consider this one as your F or your force since it is in Newton. So the clue is the unit. That's why the unit is very helpful for us to identify the given and also for us to solve the problem easily. Okay, now we can calculate the moment of a force since we already identified the given. So we will use the formula moment is equal to force times D. Again, moment is equal to F times D. And as you can see, we identified the value of your F. So we have 50 N, and your D, you have 0.25 meter. So now, let's proceed to our solution. So we will just multiply 50 times 0.25, and that gives us 12.5 Newton meter. So we will use Newton meter because the given uses Newton and meter. So it's 12.5 Newton meter. And that is the moment of a force produced in this given situation. Do you have the same answer? I guess so, because you will just multiply this one. I know it will be, this is very easy for you at this moment. So now let's proceed to another work example number 2. Now in here, we are given a figure, and then we are going to calculate the moment of a force. So figure 4.5, it shows an example or the 40 Newton, as you can see the direction. A 40 Newton force is 2.0 meters from the pivot. So how do we calculate or compute the moment of a force? Okay, so we will follow the same formula as we had a while ago. We have moment of force is equal to force or F times D. So our force is 40 Newton, as you can see, this one, 40 Newton. Multiply it by 2.0 meter as our D, as we identified a while ago in the given, your D, and also your F. Okay, so now let's go. Let's just multiply now. So to multiply, that gives us 40 Newton times 2.0 meter. That will give us 80 Newton meter or 80 Nm. So this is our answer. So I hope all of you have the same answer on the screen. I guess so. So now, I guess you got the concept already. Very easy. Just memorize the formula. Moment of force is equal to F times D. Now this time, let's talk about principle of moment. So what is the principle of moment, class? So the principle of moment, class, it states that if an object is in equilibrium, again, I'll highlight the word equilibrium for a while. I'll underline it, I encircle it rather. So again, the principle of moment, it states that if an object is in equilibrium, the sum of the clockwise moments about any point is equal to the sum of the anti-clockwise moments about that point. So the principle of moment also states about the concept of equilibrium. So again, what will happen if an object is in equilibrium according to the principle of moment? The sum of the clockwise moments is equal to the sum of anti-clockwise moments. So we can have it, as you can see in the illustration, we can just have the concept or writing the formula of it as total clockwise moment is equal to total anti-clockwise moment. Or we can denote it as this symbol. So since if an object is in equilibrium, then the sum or the total clockwise moment is equal to the total anti-clockwise moment. Or we can denote it as F times D is equal to F times D, since they are equal or the same, or in the state of equilibrium. So I want you to remember this formula. Again, this is the F times D. The left side of the equation refers to the total clockwise moment. And then F times D in the right side, on the right side rather, in the equation refers to total anti-clockwise moment. So now let's proceed to the next. So that's the principle of moment. Now, let's talk about, since we talk about the concept of equilibrium a while ago, now we will try to understand the conditions for equilibrium. So what are the conditions for equilibrium? Now, let's state with this. When a beam is balanced, we say that is in equilibrium, correct? So when a beam is balanced, we say that it is in the state of equilibrium. So if an object is in equilibrium, then first, the force on it must be balanced. Again, when a beam is balanced, or when we say that it is in the state of equilibrium, then if an object is in the state of equilibrium, the force on it must be balanced. Therefore, no resultant force. So I underline the word no resultant force. So once an object is in equilibrium, there is no resultant force. Why? Because the force on it rather must be balanced. Therefore, no resultant force. Another thing also that we have to remember, once an object is in equilibrium, the turning effects of the forces on it must also be balanced. In short, in other way of saying, there is no resultant turning effect. Again, if an object is in the state of equilibrium, there is no resultant force. And there is no resultant turning effect. So I want you to remember that very important concept. So let's now proceed to examples. Let's have an example about the state of equilibrium. So now let's do the work example. Okay, the example, the problem now here is the diagram shows a uniform half-meter rule balanced at its midpoint. So as you can see in the illustration, you have a weight of 100 Newton with a distance of 15 centimeters, and you can see the pivot, and you have a rule, and then of course you have 20 centimeters for, and then the force downward is the force or the force for the metal block. So now your question or your task is, what is the weight of the metal block? I'll give you time to do it, just like 1 minute to do it on your seat. So again, the problem is the diagram shows a uniform half-meter rule balanced at its midpoint. So the problem now is, what is the weight of the metal block? So we all know that the illustration shows, or the illustration, it shows that it is in the state of equilibrium. So what is the formula that we can use, as we mentioned a while ago? So as I posted accidentally, we will use the formula F times D is equal to F times D. In short, the total clockwise moment is equal to the total anti-clockwise moment, or F times D is equal to F times D. The first one is we have it 15 centimeters for a force of 100 Newton. On the other side, on the right side, we have 20 centimeters for a metal block. We don't know this one, so we will denote it as F. So to solve, what will we do? We will just substitute. So we all know that force on the left side, it's 100 Newton. So we have 100 times 15. So I just interchange it here. So we all know that F is 100 as given on the illustration, and D is 15. You can interchange it if you want. You can have 100 times 15 is equal to F times 20. So it's up to you. But in this case, we substitute 100 here as your F on the left side of the equation, 15 centimeter as your D. Then we don't know your F, so remain it F. And then we all know that the distance, or the D, is 20 centimeters, so we have 20. So F times 20 is 20F. That gives you 20F. Is equal to, what is 100 times, who can give me 100 times 15? So what do you think? So let's see. So 100 times 15 over 20. So you can have it 75 Newton. So that's how you do it. So again, we can use the formula of the state of equilibrium, which is F times D is equal to F times D, or the total total clockwise moment is equal to total anti-clockwise moment. Okay, then we'll just substitute the formula and do the math. Just multiply 100 times 15 and divide it by 20. So that gives us a final answer of 70 newtons. So I hope you can follow, and I hope you have the same answer on your seats, or on the screen rather. So we have 70 newton. Again, how did we get it? We just substitute it to the formula. Then you just do the math. 100 times 15 divided by 20. That gives us 75 newton. Okay, so let's go to another example. Okay, another work example class. Now, the problem here is the beam shown in the illustration below is 2.0 meters long and has a weight of 20 newtons. So it is pivoted as shown there below. A force of 10 newton acts downwards. So as you can see in there, a 10 newton acts downwards at one end. So now, what force, or F, must be applied downward in here at the other end to balance the beam? So we will, our goal here rather is to make it balanced, or to make the beam balanced. So based on the given, or based on the problem, the first step that we are going to do, class, is the first step. Identify the clockwise and anti-clockwise forces. So based on the illustration, as you can see there, we can say that the two forces act clockwise. So what are these two forces that act clockwise? These are 20 newton at 0.5 meters. So 20 newton at 0.5 meters, meter rather, and the 10 newton, as I encircled a while ago, at 1.5 meters. So 1.5 meters. So again, we have to identify the two forces act clockwise. We have the 20 newton at a distance of 0.5 meter and a 10 newtons at 1.5 meters. So once force acts anti-clockwise, then the force now is, for anti-clockwise, we have 0.5 and, or the force F at 0.5 meter. So we don't know this one. So we have to find for this force that I encircled, the F, in order to make the other end to balance the beam. So let's now proceed to the next step. So step number 2, after we identify the force acts clockwise and anti-clockwise, since the beam is in equilibrium, we have to consider that the beam is in equilibrium as posted on the screen or on the problem. So we can write the formula as total clockwise moment is equal to total anti-clockwise moment. Can you follow? So next is we have to substitute the values that we have in step number 1 and solve. So we have it here. So as we mentioned, so we know the formula, F times D. So we will add, since we have two forces act clockwise, so we will add their moment, okay? The moment force of the clockwise. So we have 20 newton times 0.5, added it to 10 newton times 1.5 meters is equal to F times 0.5 meter for our anti-clockwise. Remember the anti-clockwise, we have the force, the F, which is what we are looking for, and the D, which is 0.5. So let's just do the math. So to do the math, we have 20 newton times 0.5 meters. That gives us 10 newton meter, or Nm. 10 newton times 1.5 meter, that gives us 15 newton meters. And this one, of course, when we multiply it, that gives us 0.5 times F. So add them. So we have it 25 nm is equal to F times 0.5 meters. Then divide both sides by 0.5 meters. 0.5 meters. So we can cancel the 0.5 in here and also the meters in here. So what unit will be left is Newton. So next is we have now, that gives us F is equal to 25 Newton meter, divide it by 0.5 meters. And that gives us 50 Newton, as you can see in the illustration. So actually, so the force, so a force of 50 Newton is needed to balance the beam. Again, that means that 50 Newton is needed in order to balance the beam. And you know what, class? You can also have to work this out in your head by looking at the diagram. By looking at the diagram, then 20 Newton weight requires 20 Newton to balance it, correct? And the 10 Newton at 1.5 meters needs 30 Newton at 0.5 meter to balance it. So the total force needed now is 50 Newton. You can also do that or the other way to do or to answer the problem. Okay? So I hope you've learned so far or something this afternoon. So I will give you time to do your activity. So I hope you'll be able to finish the activity before the time. Okay? So those who did not submit or who have lacking activities, please do submit it so that I can check and record it. Thank you so much for listening, class. You can now do your activity. Have a nice day, everyone.